Okay, we were talking about some of the basic equations of flow that you need to be familiar with in terms of answering questions like how do we deal with rivers flooding. And we talked about the Bernoulli and the continuity equations, the Reynolds and Froude number. I wanted to end with the Manning's equation. The Manning's equation is one that allows us to calculate the velocity of flow in a channel based on the channel characteristics. And I mentioned last time that the channel efficiency, the slope of the river, tended to increase velocity and the resistance to flow tended to reduce it. And so what these are basically the equation, rather the variables that go into determining the average velocity of a river flow. And the resistance to flow is what we refer to as Manning's roughness, or roughness coefficient. And I'll give an example of that in a moment. Hydraulic radius is a measure of the efficiency of the channel. And again, I'll define that in a moment. The slope of the energy gradient, well, we've looked at that. Remember, the energy line is that line that the energy head, if you like, goes all the way up to the area above the water surface. That's proportional to the kinetic energy, the velocity head. And we're going to approximate the slope of the channel or the slope of the river surface to the velocity head. And that's going to be true for uniform flow. Strictly speaking, that'll vary. But as an average, that's what we can think about. So here we've got two channels, both of them artificial. But one was before concrete lining, the other was after. So which one would have the larger N value? Would it be before or after? Before, because it's a roughness coefficient. So clearly the velocity here in the concrete line channel is going to be faster, which is, of course, the main reason why we do that. The hydraulic radius, the efficiency of the channel cross-section, is the cross-sectional area divided by the wetted perimeter. And the wetted perimeter is that portion of the perimeter that is in contact with the water during bank full discharge or during when the channel is full. So here we've got a river that's got 10 cross-sectional units. Let's say 10 square meters, little channel. Okay, and it's a wide and narrow, or rather, it's a wide and shallow channel. So it's got a hydraulic radius of 0.83. Now we could look at a similar channel with the same cross-sectional area, 10 units. It's got a hydraulic radius of 1.3. Which one would have the higher velocity, the first or the second? Which? Second. Second, yeah, because, well, one, it's got a higher hydraulic radius. But two, you can begin to see that the impact of the channel size, the roughness, if you like, of the channel limits is reduced by shrinking that wide and shallow channel to more of a concave channel, a semicircle. So that's the second thing we could do to increase velocity without really changing discharge. Okay, so all in all, a wide, shallow channel is not very efficient. There's a lot of loss due to friction, and a semicircular channel has the least amount of loss in terms of the shape of the channel. The slope, well, that's a little harder to understand how it's a variable because it's basically a drop in distance per unit, a drop in elevation per unit distance. And when we think about slope, we think about the gradient of the river going down from the mountains to the sea. And so it's steep in the mountains, it gets less and less until finally in the coastal plain it's quite low. And not that we can't visualize it, but how do we change it? That's kind of the thing. Well, actually we can. Remember we talked about subsidence. So subsidence is a way we can usually inadvertently change the slope of a river. And I mentioned last time that by having a subsidence bowl and a river flowing across it, you're going to increase the steepness, then decrease the steepness. That would increase and decrease the velocity. Okay, that's usually not a good thing. But it's harder to visualize how we would do that on purpose. If we were an engineer or an engineering geologist, what would we recommend to increase the velocity? And the answer to that is related to this characteristic of a channel, the channel's sinuosity. And basically it's the degree to which it meanders or bends along its route. And so it's defined as the length of the channel versus the length of a linear distance from one part to another. You can think of it as the ratio of the length the fish swims to the bird flies. Okay? And so if it's a straight channel, then it's going to have a sinuosity of 1. And the more it meanders, the higher the sinuosity. Well, so why is that important? Well, let's look at Bray's Bayou. And let's look at Bray's Bayou in 1916, pretty much when it was unaffected. It's a little meandering valley, or channel rather, and let's compare it with 1976. Okay, the meanders are almost all gone. This channel has straightened, and so if we calculated the sinuosity of Bray's Bayou along this stretch in 1916, it was 2.7, which means the channel takes 2.4. It takes 2.4 times the distance to go from A to B. It's now a sinuosity of 1.2. It's almost a straight channel. Okay, and why did they do that? Well, because when you decrease the sinuosity, you increase the slope. And that's basically why you straighten a channel. You want to increase the slope. You've actually doubled the slope by having the sinuosity. Okay. So when we look at things we do to rivers to try to increase the velocity, we could change the cross-sectional area to change the hydraulic radius. We could reduce the resistance to flow, Manning's roughness, and we could straighten it. Now, the problem with that, I'll just kind of give you a foreshadowing of things to come. The problem with that is not that you don't decrease flooding where you channelize, you do. Now, there's actually a variety of problems related to the process, but one of the problems is that we almost never do it all the way down to the mouth of the river, which means that at some point where you stop channelizing, you end up slowing down. You never want to slow down because when you slow down, you increase the cross-sectional area. And so channelization, by speeding up the water through one stretch, will reduce flooding along that stretch, but increase it downstream. So that is one of the most obvious problems with this approach to flood control, and as we'll talk about later, that's why we don't do it so much anymore, or at least in isolation. Okay. Well, if we're going to talk about a river, if we're going to talk about what to do about rivers and how to deal with them, we need to begin with the fundamental building block of surface water hydrology, and that's the drainage basin. And the drainage basin is the same thing as the watershed. So that's basically the area that is drained past a given point. So the drainage basin is always in reference to a point. And it's defined by a drainage divide. And essentially that is the place where water either drains away from or into the drainage basin. And so when we look at a drainage divide, or rather when we look at a watershed or a drainage basin, we're really defining it in the context of a fixed feature, the drainage divide, and a variable feature, the point of reference. Because I could take that same basin, let's take this basin. Here's the watershed boundary or drainage divide, the river's flowing down that way, and that blue dot is defining the drainage divide until such time as I look at a new spot, and now I have a new drainage divide, or rather a new basin here, a sub-basin. Okay? So if I were interested in flooding here, I don't care what happens over here. Somebody else might, but I don't. Because the only thing that affects me at this point is what's upstream of me. Now, having said that, what I do here is part of what's upstream of somebody else. And so what I do in terms of maybe building a subdivision or polluting the waters affects people downstream but not upstream. On the other hand, what people do upstream affects me. So we have to look at this within the largest context. And so the largest drainage basin will actually be that point at sea level or where it enters a standing body of water. Yes, sir.
At that point, wouldn't you be interested in downstream based on what you said previously about widening a channel or straightening a channel?
Wouldn't affect me because if I sped up the velocity here, let's say.
If you slow it down downstream, then it's going to affect you because it'll build up upstream.
Well, it depends on why it's slowing down. Okay. If, for example, I channelized up here and it was slowing down here, then yes, what you do to the tributary can impact, or rather the main trunk channel can impact the tributaries. Usually, though, I'm going to treat it as independent. Take an extreme example, if I built a dam here, then clearly that would have an upstream effect. Okay, but for the most part, we're concerned with things moving downstream, and so what's upstream of me and what I'm upstream of becomes the important factor. Now, drainage basins can be big. The Mississippi River is the third largest drainage basin in the country, and of course, that is the Continental Divide. So it is quite literally dividing the flow from the Pacific Ocean to the Atlantic and Gulf Coast. And we could conversely get a little more parochial and look at the drainage basins in Harris County. Now you could consider these sub-basins if you like. Basically, here's White Oak Bayou, Buffalo Bayou, Vince Bayou, Brays Bayou, San Jacinto River, etc. Now, in the case of some drainage basins, they extend way out of our immediate area. But many of the drainage basins in Harris County, which is this dashed line, are largely confined to Harris County. So when we talk about agencies like the Harris County Flood Control, they're going to be monitoring all of these bayous and surface tributaries in the context of these subbasins. Okay, so that's how we are going to define them, and we'll monitor those subbasins by a series of gauging stations. So we've got gauging stations all over the Harris County area, and there's actually more than these, that give us real-time information in terms of the water flow, the discharge, and the elevation in order to predict flooding. Okay. Now, when we look at a large drainage basin, the upstream area is the catchment area. The discharge area is going to be where it empties into a standing body of water. And we could look at different types of rivers or different morphologies of the rivers as we go from these dissected uplands down to the coastal plain and into the delta. So notice that in this area, in the kind of the mountainous areas, we have a V-shaped valley. It's erosional. It's an entrenched valley. Down in here, we have a wider valley. You are here. And if we look at what those might look like in the wild, well, here's what we refer to as a bedrock river and a meandering alluvial river. And of course, if we get down to the discharge area, then we're looking at some kind of a delta. Okay. Now, bedrock rivers are basically, not a surprise, those rivers that are entrenched within indurated bedrock, basically material that is no longer unconsolidated sediment. Now, we're actually not going to be too interested in those rivers, although the flow equations, for the most part, that we would look at would refer to these. But these are, to a large extent, fixed boundaries. These things don't change much. They'll flood, but they're more like fixed boundary hydraulics. You can treat a channel that's in size within bedrock kind of like one that's concrete lined. Okay. Now there are some things that might make them of interest. For example, from a geologist point of view, we might look at the pattern of drainage that's superimposed on those entrenched rocks, and that'll tell us something about the kind of rocks. We have all sorts of different types of drainage patterns, and they tell us different things about mainly the lithology and the structure of the underlying rocks. Okay. Well, we're not interested in that, at least not in the context of moving water. We're going to focus on alluvial rivers, and alluvial rivers are those rivers that are not entrenched in bedrock. They are, in essence, reworking their own stream-deposited sediments. And as a result, they're much more mobile. These are the rivers that change. And so these are the rivers that we are most concerned with respect to this course, at least. Okay. Now, let's take our drainage basin. Here's our point of reference. And so let's begin to figure out how we would study a problem of flooding, because most of what I'm going to talk about is related to floods. Well, the first thing, it's got to rain. And the question then is, how much did it rain? In my house, the last couple of days, about 5 inches. Okay. What we could do is we could look at rain gauges all over the drainage basin, and we can make a contour map of lines of equal precipitation. Okay. That is, in fact, isohyethal line, or isohethal line, I think. Now, these amounts of rainfall expressed in terms of linear amounts, inches or feet, have to be for a fixed period of time. It could be a single storm. It could be seasonally. It could be annually. Okay. But notice, I'm not interested in what's over here, because my focus, for whatever reason, is that X. And so I'm only interested in what's going past that X. And any rainfall, any pollution, anything that's outside that drainage area is of no interest. Okay. Now, here is an isohyethal map for Tropical Storm Allison for Harris County. And wow, there were up to 35 inches of rain. Now, that was for a 5-day total. Okay. That's the heaviest rain we've ever seen here. Okay. Now, the other thing we could do, we could actually look at what's the probability of that particular rain, that much rain falling in a 5-day period. And, well, let's see. Down in this light blue, that's basically more than 1% a year. That's more than the 100-year rain. This is more than the 500-year rain. This is off the chart. You know, if you were to take it literally, this is like a 1,000-year rain. I advise you not to take it literally, because this introduces 2 issues. The first is that we do want to know how likely it is for that rain to fall, or that much rain to fall. And so we are concerned with how do we look at the probability statistics of rainfall. Okay, and we'll do that a little bit. The other thing is that when we look at the probability of a particular amount of rain over a particular interval, what's that based on? It's based on our historical records. And our historical records are only as good as they are predictive of the future. And one of the things we know quite clearly now is what used to be the 500-year rain is now not. It's much more frequent. Climate change is impacting our ability to predict particular events in the future. Yes, ma'am. You had a question?
So is that area more likely to flood lately now?
Oh, absolutely. Yeah, the more rain that falls, the more water is going to run off. And so you're going to look at more flooding here than here. Okay, so if we'll actually look at this as a case study a little later. Yes, ma'am.
Are you specifically talking about this area, or are we seeing this kind of all over?
Well, you mean the change?
Yeah.
Well, the change is global, but it's not the same globally. So there are parts of the U.S. where it's raining more. There are parts where it's just the intense rains are getting worse. Other parts of the U.S. it's raining less. And so the pattern of increased or decreased rainfall, whether or not it's increased average rain or increased intensity of high frequency rains, that varies. Okay. Okay. All right. So this is how we might graph it. Inches, well, notice, millimeters per hour. This is the intensity of the rainfall. And this is time. Okay, it's a histogram. It's not a cumulative frequency curve, although we could plot it as a cumulative frequency curve. And so a hydrograph plots rainfall intensity at a particular place over time. Okay, and so this is really the first thing we need if we want to predict or describe a flood event. How much rain fell. Now, you're also quite aware that condensation doesn't always fall as rain. It could be snow. Floods can occur when snow melts as well as rain falls. I'm going to focus on what happens here in Houston with rain, but recognize that there are different problems that can cause flooding that we'll hit a little bit when we look at the case studies. Now, because we're interested in flooding, we want to know not just how much rain fell, but what's happening in the channel. And so we need to think about a couple of measures of the channel flow. One is the elevation of the water surface in the channel. Okay, so that's called the stage. And so low water is considered low stage to high stage. Okay? The second is the discharge. The discharge of that river is the rate of flow, not the elevation of the water, but the rate of flow. And it's volume per unit time, so it might be cubic feet per second, which is what we use in the U.S., meters per second in the rest of the world, and you'll see these terms kind of used interchangeably. Okay. Now you might think, let's see, I've got a house, I live near a river. I don't care what the discharge is. I want to know how high that water got. I want to know if it's higher than my living room or lower than my living room. And that's clearly our goal, is to be able to predict stage. But it turns out to do that, we have to go through discharge. Because if we know the stage at a particular place, we've got no way of predicting what that stage will be downstream. If we know the discharge at that place, we can predict the discharge and therefore the stage downstream. Okay, so we're going to be talking about discharge, even though really stage is the thing that maybe we're most interested in. So here we have a hydrograph which plots either stage or discharge at a gauging station over time. And actually, here's a hydrograph here. Here's the rainfall, and here is the increase at the rising limb and then slower decrease on the falling limb of that flood hydrograph. And I could be plotting either the elevation of the water or the discharge. They'll look kind of similar, a little different though, because they're not really the same thing. And notice that the rain falls and then the water rises. Okay, this is what we refer to as the lag time. So here's our hydrograph, and here's our hydrograph. Kind of ignore these two for a while. But basically, this is the center of mass of the rainfall. What that means is when 50% of the rain has fallen. Okay, that's the centroid. This is the center of mass of the river flow when 50% of the river flow, or that related to that storm, has passed. Okay, so we could look at the time lag between these two centroids, the centroid of rain and the centroid of the river flow. Or, more commonly and easier to visualize, we'll look at peak to peak, the lag to peak, or the time lag. And that's basically from the peak rainfall to the peak stage or discharge. Okay, and that's the main thing that we use. Okay. Now, again, remember we're measuring at a gauging station that is collecting water upstream. So it should be no surprise that it takes a while for that water to get down to the station. So even though the rain has stopped, there's going to be this lag time, and that turns out to be an important measure of our being able to predict flood peaks as they go downstream. Okay. So again, the hydrograph is always in the context of a place, a gauging station. Okay. Now here's our rainfall. Okay. And notice there's a little line here, infiltration capacity. Because what falls as rain doesn't all run off, or better said, unless it's falling on concrete. And so there's going to be a certain amount of that rain that falls, particularly in the early stage, that soaks into the ground. And that's the portion of the rain that's in purple. And where does that go? Well, it goes into the soil moisture to be used by plants, and it goes into recharging the groundwater. Now, so anything above this line, when the rainfall intensity is greater than the rate of infiltration, then you have it ponding at the surface and potentially running off. But a portion of that actually just ponds. It's depression storage or surface detention. And you see it walking outside today. You see little pools of water on the lawn. And so it's only when the surface depression or detention is filled that we actually have runoff that's heading towards the river, or the bayou in this case. So only the blue is that portion of the rainfall that's actually going to run off. Okay. So the hydrograph is going to be a component. The volume of the hydrograph is just going to be a subset of the volume of the rainfall. Okay. One of the things we have to recognize is that vegetation is going to affect that relationship between rainfall and runoff. Okay. Rainfall can be intercepted. Basically, think of a canopy. You go under a tree in the rain because it's going to act like a canopy until such time as it gets sufficiently wet that you begin to see the throughfall. Okay. So some of that rain that fell on the canopy evaporates. Okay, so that's going to be a loss of rainfall not available for surface runoff. Okay, some of that will actually flow down the stem. Some of it is throughfall. So whatever gets down here will either infiltrate or run off. Okay, but by the time we get to this point, we've already had an impact of vegetation, and so when we look at changes in vegetation, changes in land use, then we're going to see how effective or not the vegetation is in modifying runoff. Okay. That surface detention, basically, we're looking at as it gets higher and higher. Well, there's two things here, I should say. There's depression storage, and that's basically the water that's standing there after water's run off. There's actually a certain volume of water that's actually on the surface. It hasn't gotten to the stream flow. And so we actually subtract that volume of water out. It's kind of in transit, but it's not in the channel. Okay. So this is the overland flow that's occurring. We've got depression storage down here, and eventually it's getting into the channel. Now, you don't have this diagram, but it's pretty self-evident. Here's our rain coming through. This is after interception, so after the vegetation has done what it's doing. Okay, and so some of it is ponding, is depression storage, and some of it is percolating through the ground, infiltrating. And some of it is running off as overland flow. Okay. Now, something happens with the water as it begins to infiltrate into the ground. And that is that quite often we'll run into layers of different permeability. And it's not uncommon for the surface layer to be more permeable than the lower layer, the deeper layer. That might be because of weathering, it may be colluvium. In fact, if you recall when we were talking about slope stability and the transition from the weathered zone to the bedrock, if you like, that was often a potential plane of weakness. Well, it's also a zone where water can flow parallel to the surface as what we call through flow. Okay? So that is actually a lateral movement of subsurface water. And some of it seeps down into deeper percolation, and that's going to get to the groundwater. This through flow we may see again. It may pop up as part of the overland flow. So recognize that the simple-minded view is rainfall minus infiltration is equal to runoff. But that little formula is rather more complicated because of different things that impact that. Okay. Well, clearly the rate of infiltration, the infiltration capacity is a major factor. That's that little red line that I drew, and it's only the water that was above that, or rather the rain that was greater than the infiltration capacity that in this model is running off. So let's look at what are some of the things that influence the rate of infiltration. Well, let's see. Surface slope, low. Low slope, high runoff. Okay. Low runoff, high infiltration. Okay. Because essentially it's not moving very fast. It has the chance at the extreme is flat. Okay. Sandy soil, that makes sense. Again, sandy soil would be more permeable. Rainfall intensity, let's keep it gentle. Okay. We want it to be rainfall less than infiltration. Soil saturation low. And the reason for that is that if the soil is saturated, it quite literally can't take any more water in. That's why when you hear the weather forecaster talk about more rain tonight and the ground is already saturated, so flooding is likely. Okay. Okay. Vegetation, the more vegetation, the greater the infiltration is because it tends to run off less. It makes the soils looser, etc. And land use, well, here I'm just going to say natural, okay, because I'm going to compare that with urbanized land uses, okay. That would be basically concrete, or making a significant portion of the area impermeable, okay. Vegetation, we're going to remove the vegetation. That's a good way to decrease infiltration. We're going to maybe have the soil saturated. Okay, that happens in rains. High precipitation intensity, heavy rains. It's raining faster than it can soak in. Soil type, well, let's make it clay because that's going to be impermeable. And slope, well, let's make it steep. Okay, all the things increasing runoff and decreasing infiltration. So these are some of the variables that impact that initial split between going into the ground or running off to the river. Now, some of these are the storm, the precipitation intensity, soil type. We pretty much live with these for the most part. But what we do change are things like vegetation and land use. And by changing that, we can impact soil type. We can even change soil slope. Okay. So some of these things that we do in the watershed can impact the amount of flooding downstream. And the short answer is we can increase flooding downstream by reducing infiltration, if no other reason. Okay. Now, the gauging stations that we have in the U.S. For monitored by the U.S. Geological Survey, Water Resources Division, are clearly mainly in the areas where it rains the most. And the nice thing is that 9 out of 10 of these are what are called real-time stream gauges. And what that means is the information that's being collected at those points, and there's many, many of them, are sent back by radio or satellite and are put on the web in every 15 minutes. So we can, right now, if I wanted to take the time, find out what the flow in Brays Bayou is within the last 15 minutes. Okay. Now, in Harris County, we've got even more, and the reason for that is we're very interested in local flooding. And urban flooding with small drainage areas with a lot of concrete means there's a very short lag time between the intense rain and the intense flooding. We don't have a lot of time. And so we need real-time monitoring, which means the USGS has some stations here, but most of the stations are operated by the Harris County Flood Control. Okay, so we have a dense network of stations here. Okay. Now, what does a gauging station look like? Well, it looks like an outhouse with cable TV. So you've got this little satellite thing up here, an antenna, and what you don't realize is that what is inside is a recorder that goes down to measure the elevation of water in the adjacent river. And there are stilling pipes in here that allow the water to maintain the same level. So the water in that little shed is going to rise and fall with the stage of the river. It is recorded and is then sent to somebody who cares. And the point here is that explains how we could get a stage hydrograph. But I'm going to go on the web and I'm going to see that not only the stage of Brays Bayou at South Main or Gessner is 42 feet, it's 1,550 cubic feet per second. There's no way that that gauging station can measure in real time discharge. Okay. So we're going to have to figure out, how do they do that? Well, let's think about stage though. Here is a typical low water crossing in the hill country, but when it's too deep to cross. Okay. And this is around Wimberley. And here we have River Road, well named. And notice there's a flood gauge here. And the intent of that is to tell you how deep the water is so you don't drive into standing water. But if you look carefully, there's debris way up here. Okay. And so the flood peak stage was pretty high. And in fact, you can see it way up here and over here. So we've got some non-stage gauge techniques for measuring peak stage. Okay. Fortunately, we can combine that with the record for that particular gauging station, and we see that elevation of 28 feet above the gauge height was well above flood stage. And in fact, if we look at it carefully, there was a 26-foot rise in 6 hours. Now that's kind of typical of flash floods we get in relatively small drainage basins where there's not much of a lag time, and in the case of the hill country where we get some really intense rains. Okay. Well, that was an impressive flood until Memorial Day of 2015 when it rose 40 feet. Now, 40-foot rise in elevation is well above the largest flood they've ever had. Okay. That other flood, it was here. Okay. The 2015 flood is one of the worst floods that's hit the hill country, ever, in terms of human loss of life, etc. And the problem was, it was a 40-foot rise, well above what was predicted, and it came at night. So the peak was around midnight. And quite literally, people were trapped in their homes. One whole family, the flood lifted the house and took the whole family downstream. They never found the children. So it's one of those things where we have to think, what could we do differently to try to deal with this type of problem? Okay, and one of the problems is we can't necessarily assume the maximum historical flood is going to be the maximum flood that we need to deal with. Okay, so how do we go about dealing with discharge? If discharge is so important, even though stage seems to be what is easiest to measure and easiest to understand, well, we're going to go back to that continuity equation, and we're just going to say velocity times cross-sectional area. Okay, so if I can measure both, I'm okay. The only problem, and well, actually, let's do that. Here, the stage is 1.2 feet. The velocity is 1.5 feet per second. Cross-sectional area is 70.8 cubic feet. Discharge is 100 cubic feet per second. That rises to 3 feet per second. It goes to 3 feet elevation. We went from 1.2 stage to 3.1 stage. We increased stage by about 2.5 times, but we went from 100 CFS to almost 800 CFS. Okay. Now, what that tells me is that the relationship between stage and discharge is not linear. And it's not linear because velocity is changing. Look how much more, the velocity here is very low, the velocity here is much faster. Okay? So, what are we going to do? Well, we got to measure velocity. Let's do that first. And the way we're going to do that is, well, one way, what we used to, was drop a sounding weight. We have these little cups that spin around. The rate at which they spin is proportional to velocity. And literally, we have a click counter, which counts the numbers of clicks and says this is so many feet per second. Now, notice there's a cable running across here. That's because if you want to measure it in shallow water, it's easy, but if you want to measure it in deep water, you've got to either ride that gondola or you need to figure out how to measure it otherwise. And so this is where the intro level intern hydrologists end up getting their stripes. So here is a hint. Remember that velocity profile that we talked about for laminar flow? It's logarithmic. The mean flow is typically at a relative depth of about 40%. Okay? And what that means is that if this is the surface, then if you go 40% from the bottom and just measure the velocity there, then that's pretty good first approximation. Okay. Well, okay, that means that one measurement along the point, probably not the best way, but is an approximation of velocity. Okay. Now notice we don't deal with laminar flow. The problem is that the velocity changes with width as well. There's drag on the bottom. The channel is fastest at the surface. And so we're going to have to measure at a whole bunch of places. In fact, notice there are these little dots because we don't just measure at one depth if we can avoid it. We measure multiple depths all along in here. And so there might be 30 measurements along this particular cross-section in order to get the average velocity. So that's a lot of work. Okay. And so we multiply the velocity times the cross-sectional area, and we get the discharge that way. Okay. And this is just another way of saying it. Well, wouldn't it be nice if we didn't have to use that little current meter? And so we actually now have a method where we can use, look at the Doppler effect. We've got a boat on the surface, and the boat can measure the velocity of the water and the depth as you go across. And so at that point, you actually have now a way of measuring the velocity and the cross-sectional area in a way that's both more precise, more accurate, and easier to obtain. So increasingly we're using this type of measure. Okay. So here we've got brazed biome, a stage hydrograph, and there's the discharge hydrograph. The peak is at the same point, but the shape is rather different. Notice we go from less than 100 CFS to 5,500 CFS, whereas we went from 28 feet to 35 feet. Again, I took this off in real time. Here's the trick. We can measure the elevation, and we can do it at a gauging station. But it requires somebody in a boat or a gondola or in wading boots to measure and calculate the discharge. Okay. So we did it once. And we do it a whole bunch of times until we find that relationship between discharge and elevation. And that's what we call the rating curve. And so the discharge rating curve is basically a way of relating and therefore predicting discharge from stage. So once the rating curve has been established, then we don't have to measure it. When that signal comes in saying the stage is something, the computer takes over. Looks at that curve and takes it on. Yes, sir.
Are the velocities measured annually to account for like the stream profile changes?
Oh yeah, absolutely. And the thing is, all these numbers are taken. And so one of the questions that you may be going towards is the rating curve constant?
Well, of course it's not.
And well, no, there's two things. Constant for a particular place, and if not, are there seasonal variations? And the answer is yes. There are rating curves for the rising stage and the falling stage. They're what we call looped rating curves. It goes up like this and down like this. So it is more complicated than this, but that is what they do. Okay, and they obviously have to check it to make sure that, particularly after a flood, there haven't been changes in the shape of the cross section, for example. Absolutely. But the other point is, this is only good for that gauging station. You can go half a mile downstream and it's irrelevant because the geometry of that particular channel and that valley may well be completely different. And in fact, if they move the gauging station, they have to redo it. Okay. But by having a discharge rating curve, we now can get a real-time estimate of discharge. This is just to show that in general it's a logarithmic function, so it's not a surprise you can see that here. If I were to plot this on log discharge or log stage, I could get a straight line on that. Okay. Now, what we're trying to do is figure out, well, actually what we're trying to do is predict that hydrograph. But we have to recognize that hydrograph consists of different sources of water. Okay? So, for example, there's base flow, that flow that comes in from the groundwater. And that's going to be the low flow even when there's no rain. Then we have something called Horton overland flow, or infiltration excess. And that's what I alluded to when I said when the rainfall is greater than the rate of infiltration, we have overland flow. It just can't sink in fast enough. It has to move overland. But then we've got two more elements, and I'll have to define each of them, but subsurface storm flow and saturated overland flow. Okay? So clearly, this is an enhanced flow beneath the ground. Think of probably through flow rather. And here's something, it's still overland flow, but it's not exactly Horton overland flow. So let's see what that might deal with. Base flow is easy. Base flow is basically when we've got the water table discharging into the river. And of course, it's the main source of stream flow between storms, and it is characteristic of perennial streams. If there's always water in the river, that means that during a significant portion of the time, that water is being supplied by groundwater or base flow. Okay. Now, in this particular example, we've just kind of separated the hydrograph into storm flow and base flow. And notice the base flow rises. And the reason for that is that there's infiltration that's going on here, and that's causing more water to discharge. So as the water table rises, it increases the pressure to discharge into the river. So this rise is related to the recharge during the storm. And then from here on, this is basically just the depletion of the groundwater. We call it a groundwater recession curve. And basically that's just the water table dropping and the stage dropping it with you. Okay. So here's that 2001 hydrograph, and so there we can kind of sketch in what component is storm flow and what component is base flow. And there's actually different techniques for sketching it, but certainly it's easy enough to visualize. Okay. Now, the problem comes when we want to dissect the stream flow. So here's the hydrograph. Here's the base flow. Now we've got some of it's Horton overland flow. More of it's actually saturated overland flow. And there's a big chunk of it that's subsurface storm flow. So we got to figure out what exactly are those components, because they are, in this particular example, the dominant source of storm flow. Okay. Now Horton, we'll start with the easy. This is, as I showed before, as infiltration capacity is measured by this red line, whenever rainfall intensity is greater than the rate at which it can soak in, it runs off. Okay. So all of this would be infiltration, and all of this would be Horton overland flow. Now, notice the infiltration capacity changes through time. It decreases during the storm, and that's because it's getting more and more saturated. Okay, so it just can't soak in. If things are dry, you got rapid infiltration. Once it's saturated, very little. Okay, and that's what we've described here and here. Now, Horton overland flow, it's one of the things I like about it is it's easy to understand, it's easy to visualize. Okay? And so one of the things that happens is as you get, let's say this right here is the drainage divide. And it may be just a shoulder of a little gully. But the water that, and the rain that falls here, the excess rain is going to run out with surface water. And whatever falls here, we don't care. Now, the uppermost part of that, from that crest to some distance, you're going to have sheet flow. It's just basically moving down as a sheet. But as the water gets deeper, and of course it's getting deeper because there's more and more water falling upstream, if you like, or upslope, at some point you reach a critical point where you begin to have erosion. And once you begin to erode, the erosion starts to be channelized and you're getting gullies. So you have this critical threshold here, okay, where you're beginning to have active erosion, and this is typically gullying. We'll talk more about this in another lecture. At some point, we have the potential for deposition of sediment at the base. Or it could continue to erode all the way to the channel itself. Okay? But the idea of sheet flow with no erosion and then gullying and then finally coming over, easy to visualize. And when we go to the desert Southwest, we can see that. We can see kind of a smooth slope, and then as you get farther down the slope, you get little gullies, and little rills, rather, is what they're called, and then they coalesce into larger gullies, and then eventually they come into the creek or whatever. Okay. Now, let's look at what else is it. Well, okay, look at this. Subsurface storm flow. This is the flow that's moving. This is the through flow. Okay. This is the stuff that's moving through that upper soil horizon, that upper primeval soil horizon. And it's basically a combination of matrix flow and macro flow. Matrix flow is just kind of working through the matrix, but look at this water coming through here. That's macro flow. It's probably a burrow, could be a rooted area. So there are areas where the water can really just gush out, and it's moving through, and it's going to hit the river. Okay. Now, in many areas, particularly humid areas, that is the dominant mechanism for rud flow, stream flow. That water that comes in through that little narrow zone. It's important because it's one of the variables, one of the more important variables to initiate slope instability. There's a lot of flushing of nutrients and pollutants in that zone. So water quality issues are important. And of course the hydrograph is important as well. Okay. So here is that water that's coming along here. Okay. Yeah, basically flowing in the shallow area but saturated. Now, look what would happen if that water table continued to rise and intercepted the surface here. Okay. We're going to have a saturated area that when rain falls, it has to run off. In fact, there's water that's returning. And where is it coming from? It's returning from the subsurface. Because the water table has now intersected the surface, and we've actually got like a spring. We've got groundwater that's discharging onto the surface. Okay. So we've got two sources of overland flow that's coming here. The rain that falls on that wetted area and the water that's emerging from that wetted area. And those two together are the saturated overland flow. Okay. So here's a case where we don't have any Horton overland flow. We've got mainly saturated overland flow and then some shallow and deep subsurface storm flow. Okay. Now, here's again an example. Here we've got only Horton overland flow. It's just flowing over the surface. Everything that infiltrates is gone. Here we've got saturated overland flow. And we've also got subsurface flow that's coming in, particularly along here where we've got this break between horizon 1 that's more permeable and horizon 2 that's not. This is basically a perched water table. You can think of through flow, subsurface storm flow, as a little perched water table that's flowing down the weathered zone, or whatever is controlling that break in permeability. Now notice here, this is called the variable source area. So let's see what that means. Clearly, as the water table rises, the area where you're going to have saturation is going to begin at the margin of the stream and move up from the bottom of that stream. And it's going to come up. In this case, it may vary seasonally. So It's right along in here. It's almost restricted to what would be the channel in the summer. But then in the autumn, it gets wider. It's getting wider because it's getting higher. It's getting higher because there's more rain in the autumn. And finally, right after snow melt, we get a lot more area. This is clearly an area where snow is melting and it's soaking into the ground. It's causing a rise in the water table. So these three areas are areas that are saturated at different times, and that's what we mean by variable source areas, because any rainfall, any rain that falls on these areas will run off. It can't soak in because, in fact, the water is coming out. It's completely saturated. Okay? So that is the source area for rain. And we could also do it beginning in a storm in the end. Remember that rise in the water table? Well, here it is at the beginning of the storm and at the end of the storm. So we can have seasonal variations in the water level and storm variations in the water level. Okay. Now, it turns out that this particular type of hydrograph and this particular type of model is typical of humid regions. It's the most common. Horton overland flow really doesn't exist very much around here. The reason is we have so much vegetation, okay, that in undisturbed areas, the water is infiltrating, and the only time when we have runoff is in those areas where we have the emergence of water in the ground. Okay. Conversely, Horton overland flow is the dominant process for arid regions and semi-arid regions. Okay. Now, things change here as we urbanize. Horton overland flow is typical of urbanized areas because we've removed the vegetation for the most part. We've concrete lined it. We've made infiltration go to zero. Okay. And so the relative importance of these different flow components of the hydrograph will vary depending on the natural environment, the natural climate, if you like, and also the urbanized environment. Okay, and so we have computer models that basically will model variable source area, and essentially they're predicted on the basis of the rise in the water table. Okay, so this is actually looking at how much the water table has risen, and the lightest blue, the greatest area, is 3 meters above the stream. So what we're saying is the water table has risen 3 meters higher at the stream level. And what that translates to is an increasingly large area of saturated ground. Okay. Now, we know from freshman geology that not all rivers are fed by the groundwater. In humid areas, they are. Water table is basically recharging the rivers, is what we call a gaining or effluent stream. But in arid regions, the water table is low. It's the only time there's a connection between groundwater and surface water is during a rain, and the water is soaking into the ground. The water in the river, rather the river is no longer a discharge area, it's a recharge area. Okay, it is recharging the ground. Now it turns out that little area at the interface between the base of the channel and the discharge of the water into the channel from the groundwater is called the hyphoric zone. And it's a zone of mixing. And it's not very thick. It's inches to a foot or two in thickness. But it's really important because there are a lot of changes in the oxygen and reducing environment biogeochemical changes that enhance microbial activity and chemical transformation. So what it does, it will increase the rate at which organic contaminants degrade. It'll also remove certain metals from the groundwater by causing the metals to precipitate on the sediment. Okay, so that's actually an important role biologically and in terms of water quality. Okay. Now, essentially, initially we're looking at high oxygen coming from the surface water and low oxygen from the groundwater. Groundwater is largely oxygen depleted compared to surface water, which is oxygenated. In turn, we have aerobic microbial processes going on in the upper part and anaerobic in the lower part. So we've got oxidation reduction. So if you have nitrates, for example, that are coming through, they're changed to ammonia. If you have ferrous iron coming up, it's changed to ferric iron. Ferrous iron is iron in the reduced form, and it is mobile, and it will be carried through the groundwater until such time as it's oxidized to ferric iron, which is immobile. Oxidation of iron results in the precipitation of iron oxides, and it's a way of extracting iron and other metals as well from the groundwater onto the sediment. Now, that's not always good because this can happen in lakes and the like, and so heavy metals that maybe come into a lake will attach to and be changed and fixed onto sediment. Clays especially are very absorbent because of their high surface absorptivity. And so we've got this zone at the bottom of some of these lakes that are basically removing bad stuff from the water, but now it's concentrating in the sediment. And so we often have very highly polluted sediment at the base of some of these areas. PCBs are particularly bad about doing that. Okay. And biologically, it's just a unique area. Okay. Certain organisms only live in that area. Okay. So let's just imagine what would happen if that was concrete lined. Well, we would reduce flooding at that place. But we also reduce the exchange of groundwater or interaction of groundwater and surface water. We have no groundwater recharge. We've lost our habitats, all sorts of habitats. And so the environmental issues related to particularly concrete lining are pretty substantial. Okay. Now, if we look at the source of water in a perennial river, for most of the year it's groundwater, base flow. Those little spikes are the rains. An ephemeral river, it's an influent river. There's no groundwater recharge. I'm sorry, there's no groundwater base flow. So we have rain, and then it soaks dry. Rain, and it's dry. So this is our ephemeral river. And this is, of course, a hydrograph. This is an annual hydrograph of snowmelt. Or better said, it is the hydrograph of a river which has as a major component of its overland flow snow melting. Okay. So climate makes a big difference in terms of how we're going to deal with these issues. Okay. Now, flooding is a problem, as we've talked about earlier. In the U.S., this is the biggest loss of life and dollar values, $6 billion per year. There's all sorts of impacts And increasing urbanization, development in flood-prone and coastal areas are basically increasing our vulnerability to the risk of flooding. So if we're talking about risk, we need to know, well, how bad is it? And of course, risk depends on frequency and magnitude. Now, once you've established what the risk is, you have to say, is it an acceptable level of risk? The role of the scientist is to give the public and the planners an idea of the risk. The public and the planners and the politicians have to decide, and the individuals, depending on what decisions are being made, what is an acceptable level of risk. But we cannot make decisions about acceptable level of risk until we understand what our choices are. So we need to know not only how bad is the flooding, but how frequent is the flooding. And so for that, we're going to use recurrence interval and exceedance probability. The same concepts we did with earthquakes and with volcanoes. Okay. Now, when we talk about recurrence interval, and this is a review from earthquakes, but the annual recurrence interval is the average number of years between events of equal or greater magnitude. Okay. So the 100-year flood is one that occurs on the average once every 100 years. Okay. And we can calculate that by this equation. One of the few equations I'll ask you to remember. And that is, you take the number of years of record plus 1, divide by the range. So let's just say we've got 99 years of record. The largest flood in that 99-year period is going to have a recurrence interval of 99 plus 1 divided by 1. It's the 100-year flood. Okay. Now, the probability of an event of a particular magnitude being equaled or exceeded in any 12-month period, and actually when I said the annual probability, we use that term, but we really mean within any 12-month period, because the water year is different from the calendar year, from the tax year, and so we're just talking about a 12-month period. It's the reciprocal of the recurrence interval. So the 100-year flood has a 1 in 100 or a 1% exceedance probability, probability being equal or exceeded during that 12-month period. Okay. So we could look at frequency, and we could look at exceedance probability. Now, one of the problems is a 10-year flood has a 10% probability of occurring. The problem is the 2-year flood doesn't have a 2%, it's got a 50%. It's 1 divided by 2. 1 divided by 50 is 2%. 1 divided by 100 is 1%. We get sloppy in our thinking, so we often forget that it's just the reciprocal. It's 1 divided by the recurrence interval. Now, as it turns out, there are certain recurrence intervals, certain exceedance probabilities that are used for flood insurance purposes. Okay, and you will not find in more recent publications the map of the 100-year flood. You'll find the map of the 1% flood, and the 10% flood, and the 0.2% flood. And the reason, quite simply, is that people can understand the probabilistic nature of flooding better if it's expressed as a percent probability and not average interval between floods. Because, like it or not, when you say a 100-year flood, many people think it occurs once every 100 years. So the best thing you can do is buy up flooded property after a 100-year flood, because you got 100 years to go. And it happens all the time. And so if you say there's still a 1%, and we'll see later there's actually a much larger percent flooding if you're looking at longer rates of time, then people better understand what the risk is involves. Okay. Now, there are a variety of ways that we can determine risk. Stream flow data, regionalization, digital models, probable maximum flood. And so I'm just going to look at one today, this case study, which by the way is also going to be homework assignment 2. Okay. And here is a histogram of peak annual discharge. This is the maximum discharge, maximum daily discharge in a water year. Okay. And it goes through 1999. And there were 2 floods we were particularly interested in as they have impacted a little town called Simonton on the Brazos River. The problem is, what is the probability of floods this big occurring again? Well, for people who moved here, they said, wow, we just never understood it. And of course, the subdivision was relatively new. We just never seen anything like this. But of course, if you look back here, you say, well, it's not that uncommon. So just how uncommon is it? Well, what you do is you look at the peak flood, peak annual discharge for each water year of record. And then you rank it from the largest number 1 to whatever, in this case, 76 years of record. And so then, when you've done that, now I've ranked them from biggest to smallest. I look at the recurrence interval. The recurrence interval is n plus 1 divided by n. N, 76 years. So all of these will be 77 years divided by n. So 77 years is the recurrence interval for the biggest flood of record. 1 divided by 77, 1.3%. That's a 1.3% probability, exceeding probability. And it goes on down the list. Okay. Now, when you plot that, oh, by the way, these reds are the floods of interest, 5th and 10th largest. So we got quite a few. And so when we plot the discharge versus recurrence interval, and this, by the way, is actually we could do probability over here, decreasing in that direction. We see that there's a 6.5% chance of the biggest flood here occurring in any one year. There's even a higher probability of this one occurring in any given year. Okay. And so what it tells us is that this particular place has a serious flooding problem. And it's only going to get worse, in part because these data, going back to 1920, may not be representative for the future. So we're going to use that as a case study. And notice we've taken these data and we've extrapolated it. We've extrapolated it to 100 years. So you might ask yourself, how do they know what a 100-year flood is if you don't have 100 years of record? Well, you hope that you get a relationship that you can extrapolate from what you do have to that particular relationship. So that's what we would do here. Oops. We would extrapolate from the 50-year flood plus all the others to that 100-year flood. So we can use historical stream flow data using this technique to determine the 100-year flood with all the caveats that come with it, but that will be part of your assignment after spring break. Okay, you have a minute? It's on me. See you.